So, in this lecture, we will discuss the problems related to impulse signal, basically continuous time impulse signal, and we'll see how we can apply the properties of impulse signal to solve the problems. So, in the first question, x of t is given by integral 0 to 5 del of t sine 2 pi t into dt. Okay. So, on the right side, you can see some basic properties of the impulse signal. Del of at is equal to 1 by modulus of a del of t, and x of t is actually known as a scaling property of continuous time impulse signal. And the next one is known as sampling property. X of t into del of t minus t0, which is given by x of t0. Okay, so that's only difference if you observe the LHS and RHS. Here it is x of t, and you come to the RHS as x of t0 into del of t minus t0. And third property is also very important to solve the problem, is also known as sampling or shifting property. Here you can observe the same thing if you integrate from minus infinity infinity, or within the limit del of t where del of t minus t0 exists. It's simply x of t0. There is no term called del of t minus t0. So closely observe these two properties. There's a slight difference between these two properties. There is no integral sign in the second, and in third one you can see the integral sign. Okay, and the RHS also the terms are similar, but there is no impulse expression in the third property, that is in the shifting property. Okay, now we can see that this is an impulse signal multiplied by a sinusoidal signal. So del of t means it's an impulse signal which exists at t is equal to 0, and this is the impulse signal del of t which exists at t is equal to 0, whose area is equal to 1. So integral minus infinity infinity del of t, if you integrate you will get 1, and the signal magnitude is 0 when t not equal to 0. Okay, that's the meaning of impulse signal, continuous time impulse signal. And in this particular expression, the integration was only from 0 to 5, and we don't want to integrate it from 0 to 5 because the signal exists only at t is equal to 0. So I can simplify this integration, or we can apply the property. If you integrate it 1, 2 and 3, we can apply the shifting property, which is simply x of t0. That is, we will evaluate x of t at t is equal to 0. If you apply this particular property, it's integral minus infinity to infinity x of t into del of t here. Okay, uh, here t0 is equal to 0. So simply you can write x of t at t is equal to 0. So you will get x of 0. So in place of x of t, it is sine t here. So we can evaluate. Don't get confused with the expression here. X of t is given as a function. Anyway, the log t is multiplied by a function. So we can evaluate this at t is equal to 0. So we'll get sine 0, which is equal to 0. Okay. So by applying the shifting property or sampling property, you can reduce the expression, and you will get sine 0 is equal to 0. In this question, there is no integral sign. X of t is given as a function of del of t plus 3 into e raised to minus t. So here we need to apply this particular property. There is a sampling property, x of t into del of t minus t0 into is given by x of t0 into del of t minus t0. And here this t0 is given as minus 3. So we can draw this waveform del of t plus 3, del of t plus 3 exists only at t is equal to minus 3. So this is the impulse signal which exists at t is equal to minus 3. Okay, and the area of the impulse signal is equal to 1, and del of t plus 3 is equal to 0 when t plus 3 not equal to 0 or t not equal to minus 3. So in all other values t, the function magnitude is 0. And if you integrate this function from minus infinity to infinity, del of t plus 3 dt, you will get 1, because area of the signal is equal to 1. So if you simplify this particular expression, you can write it's x of t0 into del of t minus t0. So in place of x of t, here it is given e raised to minus t. So I can write del of t plus 3, and you can evaluate e raised to minus t at t is equal to minus 3. So it becomes e raised to minus into t is equal to minus 3. So you can write minus 3 del of t plus 3. So it becomes e raised to 3 del of t plus 3. So you cannot simply write e raised to 3 or e cube, because there is no integral sign. So the resultant signal is something like this, which exists at t is equal to minus 3, and whose amplitude is e raised to 3 into del of t plus 3. And here it is simply del of t plus 3, whose area is equal to 1. So that's the difference. Okay, this is actually a signal, not a magnitude. But in the previous case, you can see that this is not a signal. Final magnitude is 0. So x of t, it's 0. And if you draw the waveform, it's completely 0. In all values, it's 0. 0 magnitude. X of t is equal to 0. Now you can see that this is x of t, which exists only at t is equal to minus 3. So that is a difference. Here x of t is equal to e cube del of t plus 3. So this is a signal which exists only at t is equal to minus 3. Now we can see another signal, which is del of t minus 3 into t minus 3 the whole square, and integral from minus infinity into infinity. So you can apply this shifting property, and here in place of x of t, it is del of t minus 3. So del of t minus 3 means I can draw this waveform. This is 0 and this is 3. So signal exists only at 3. So del of t minus 3, and del of t minus 3 dt, or area of this particular impulse signal, is equal to 1, and signal does not exist when t minus 3 not equal to 0 or t not equal to 3. Okay, and we can simplify this, t minus 3 the whole square at t is equal to 3. So by applying this theorem, x of t0, so here expression we need to evaluate at t is equal to 3. So if we substitute 3, it becomes 3 minus 3 whole square, so 0 whole square. So final answer will be 0. So if you take this particular question, it actually contains two parts. So I can split the integration. It's from minus infinity to infinity, del of t cos t dt plus integral minus infinity to infinity del of t minus 1 into sine t dt. Okay, again you can apply the shifting property here. Okay, shifting property of continuous time impulse signal, and we know that the expression reduces to x of t0, or we can evaluate the function, the given function at t is equal to t0. So in the first question, this is an impulse signal which is del of t. So we know that the impulse signal exists only at t is equal to 0. This is a unit impulse signal, that is del of t, and whose area is equal to 1, and integral minus infinity to infinity del of t dt is equal to 1, and del of t equal to 0 when t not equal to 0. Okay, so we can evaluate the first part at t is equal to 0, and if we compare the second part, okay, it is del of t minus 1. Del of t minus 1 exists at 1. So del of t minus 1 exists at t is equal to 1, and the area of this particular signal, shifted impulse signal, is equal to 1, and the signal does not exist when t minus 1 not equal to 0 or t not equal to 1. So the second part, you can evaluate at x of t0. So sine g you can evaluate at t is equal to 1. So it becomes cos 0 plus sine 1. So cos 0 is 1, so 1 plus sine 1. So if you take this particular expression here again, del of t, so again I can apply the shifting property. So if you are multiplying with an impulse signal, finally you need to evaluate at t0. So here t0 is equal to 0, or you can say del of t is a signal which exists at t is equal to 0, del of t which exists only at t is equal to 0, and the area of the impulse signal del of t dt is equal to 1, and del of t is equal to 0 when t not equal to 0. So we can conclude that the integration we can evaluate only at t is equal to 0. We don't want to integrate from minus infinity to infinity. So it becomes e raised to 0, which is equal to 1. Now we can evaluate another question, which is x of 2 minus t into del of 3 minus t. Here, the impulse signal del of 3 minus t is given not in the standard form, so I need to rewrite this. So del of, if you take a minus 1 outside, it becomes t plus, sorry, t minus 3. Okay. So if you look at this particular expression, it is similar to del of a into something, and del of at is simply 1 by modulus of a into del of t. And if you apply the scaling property here, so we'll get, it becomes 1 by minus 1 modulus into del of t minus 3. So you can write del of t minus 3. And in the expression, if you substitute this result, integral minus infinity to infinity x of 2 minus t into del of t minus 3 dt. Okay. And del of t minus 3 means a signal which exists only at t is equal to 3. So function which exists only at t is equal to 3, and del of t minus 3 becomes 0 when t minus 3 not equal to 0 or t not equal to 3, and the area of this particular impulse signal is also 1. So we don't want to evaluate the function for the entire limit. We can evaluate the signal only at t is equal to 3. So it becomes x of minus 1. Okay. So this is another question similar to the previous one. Here the impulse signal is given del of 2t minus 2. So we need to convert it into standard form. So we need to write del of 2 into t minus 1. Okay. So by applying the scaling property, del of at is 1 by modulus of a into del of t. That is the scaling property of impulse signal. So you can write 1 by modulus of 2, that is 2 del of t minus 1. So del of t minus 1 means minus 1 means the signal exists only at 1. So this is the signal which exists at del of t minus 1, and the del of t minus 1, if we integrate from minus infinity to infinity, is 1, and del of t minus 1 is equal to 0 when t minus 1 not equal to 0 or t not equal to 1. And you can substitute the result in the first expression, so it becomes integral minus infinity to infinity e raised to minus t 1 by 2 into del of t minus 1 dt. So 1 by 2 is a constant, and remaining term, if you write integral minus infinity to infinity e raised to minus t del of t minus 1 dt. By applying the shifting property, we can evaluate this particular function e raised to minus t at t is equal to 1. So it becomes 1 by 2 e raised to minus 1. Okay. So this is another question. Here it's given del of 1 minus t. Again, this is not in the standard form, so we need to convert del of 1 minus t in standard form. So we can write del of minus 1 into t minus 1. Okay. So if you rearrange this or by applying the scaling property, a becomes 1 by modulus a. So here a is equal to minus 1. So you can write minus 1 modulus del of t minus 1. So it's simply del of t minus 1, and del of t minus 1 means a signal which exists at t is equal to 1. So this is a signal del of t minus 1 and whose area is equal to 1, and which does not exist when t minus 1 not equal to 0 or t not equal to 1. And if you substitute the result in the expression, it becomes t cube plus 4 into del of t minus 1. So we can conclude by applying the shifting property. So we can evaluate this function only at t is equal to 1. So it becomes 1 plus 4, which is equal to 5. So this is all about inverse signal. And closely observe that when it is del of 1 minus t or when it is del of minus t, don't directly apply the property. First apply the scaling property and make the equation in standard form. So similar question we discussed in the previous one, del of 2t minus 2. First make it in the standard form and apply the scaling property, then only apply the property. So same concept is here. Again del of 3 minus t. So we need to make del of minus t into plus t, then only we can apply the properties.